Hello everyone. We will be explaining our concept, weather-aided AI calibration of monsoon rainfall. Here are the objectives. Accurate precipitation forecasting in some parts of India is hindered by sparse, ground-based radar coverage, inaccurate satellite rainfall estimates, and the limitations of existing weather models. These gaps pose serious challenges for disaster and preparedness and water resource planning. The idea is leveraging AI-driven approaches to integrate diverse, ground-based data sources and to improve satellite estimations of rainfall, transforming how we understand and respond to monsoon variability in vulnerable regions. The impact. We want to provide farmers with regional, adaptive tools that will improve their agricultural efficiencies, flood mitigation for local governments in Maharashtra and Odisha, which is where we've placed several weather stations as a template for expansion in other regions of India. We are also improving the data availability in these radar gap areas.
Thanks, Maura, for that introduction. Uh, India's radar coverage is quite uneven, with many of the regions, especially the northwest and central eastern India, lacking consistent radar observations. So, in these areas with incomplete radar coverage, NASA's iMerge must substitute, but generally it's not as accurate. In most of these areas, so on the left you have Rajasthan, Punjab, and Haryana, and on the right, Odisha, a significant population of this region is employed in farming or sort of industries associated with farming. Therefore, we hope this model would help them and generally help the scientific community in the assessment of rainfall in these regions. So, the integrated multi-satellite retrieval for GPM, the iMerge, essentially merges satellite microwave precipitation for similar to radar, and it's interpolated by infrared cloud data. So it's a tenth of a degree at half our resolution. The GFS, the Global Forecast System, is a global weather model that's ran every 6 hours with hourly forecasts at like a quarter degree and with like an hourly resolution. And then the weather stations itself were set up by the City University of New York. It's funded by the US State Department and the National Science Foundation. We've currently installed 23 of these stations across 8 states. So for the purpose of this project, we used weather stations from 5 of these places across Maharashtra and Odisha. So these record precipitation against 15-minute intervals, and they're really accurate to these specific areas. So they're recorded across the year, and as you can see, the peak rainfall across the monsoon happens right here between May and November. And typically during June to September, you have the ITCZ, the Intertropical Convergence Zone, that shifts northward over the Indian subcontinent because of strong solar heating. So this northward shift essentially moves the ascending branch of the Hadley cell over India. And the result is this warm, moist air across the Indian Ocean being drawn towards this low pressure land over land, creating these southwest winds that bring the heavy rainfall that's uh, predominant to India. So Maharashtra receives monsoon rainfall from June to September, with temperatures sort of ranging from 20 to 30 degrees throughout the year, influenced by these southwest monsoons. Two of our weather stations were used, one in Mumbai and the other in Palghar, called the GEV. They're indicated in red. The precipitation radar is marked in green. Physiographically, it's part of the Western Ghats, especially GEV in this case. Odisha experiences monsoon rainfall from June to October, with slightly warmer temperatures and moisture due to its proximity to the sea, and generally a wide range of climatic conditions due to the proximity to the Bay of Bengal. Three of our weather stations were used, XIM, Bakul, and KIT, and those are sort of indicated in red with the corresponding precipitation radar in green. And its terrain is dominated by the coastal plains and the eastern Ghats. So two very different types of physiographies and terrains, and that's the reason that we pick these specific points. Anyways, over to Lily to explain our model and results.
Thanks, Aryan. On this slide, we introduce the different data sources used in our analysis. We have iMerge, which you heard about before. That's NASA's satellite-based precipitation product. And alongside iMerge, we incorporate several forecast variables from the Global Forecast System. First, we have convective available potential energy, or CAPE. CAPE quantifies the positive buoyant energy available to a rising air parcel. So it's a measure of atmospheric instability, and it provides an estimate of potential updraft strength in convective storms. Meteorologists use this to assess both probability of thunderstorm development and potential intensity of those storms. Next, we have convective inhibition, or SIN. SIN represents the negative buoyant energy that suppresses vertical motion. So a strong SIN layer can delay or even prevent convection. And lastly, we have total precipitable water, or TPW. TPW measures the total amount of water vapor contained in the vertical column. A higher TPW will typically correspond to greater potential for precipitation, especially in a monsoon environment. This slide compares the regression performance of iMerge at two temporal scales. We have on the left the half-hourly rainfall, and on the right we see daily aggregated rainfall. So you'll notice in the half-hourly plot there's a lot of variability. We have a wide scatter, R-squared is very low, while as in the daily aggregate plot, the relationship between station rainfall and iMerge is stronger. We have a steeper slope, the spread is reduced, and the R-squared value is notably larger at 0.5. This slide shows the daily aggregated regression plots for 3 individual stations. Again, when we aggregate to a daily rainfall timescale, we see an improved relationship compared to the half-hourly, but we still see variability among the stations. And this is expected. Each station measures rainfall at a single point, while iMerge represents precipitation averaged over a much larger satellite area. For our machine learning model, this reinforces our choice to rely on daily aggregates when visualizing baseline, and to also incorporate those additional weather features such as CAPE, SIN, and TPW, so that the model can account for the atmospheric conditions under which iMerge deviates from station measurements. That said, I'll pass it on to Victor, who's going to tell us more about machine learning.
Thank you very much, Lily. Now, I'm going to be following with neural network architecture. So let's take a look under the hood. To solve some of the problems of inaccurate satellite rainfall data, we didn't just want to throw numbers into a black box and see what will happen. We wanted to fuse observation with physics. On the left, you will be able to see our inputs. We are not just taking raw satellite data, we're actually combining it with atmospheric variables. We fed this into a deep neural network. We structured this as a funnel. It starts from 32 neurons, then it compresses that knowledge down to 16, 8, and finally we get the single prediction. We deliberately kept this model light just to prevent it from memorizing data. The goal here was to teach the computer to look at the satellite image, check atmospheric conditions, and say, hey, the satellite sees rain, but the pressure is too stable, so it's probably just a false alarm. Now here, you can see the results. This is the moment of truth. We ran 3 scenarios to see if we could beat the raw satellite data. On the left, which is the baseline, you can see the raw iMerge satellite data versus the ground stations. The MI, which is the error, is around 22. In the middle, you guys can see the version of the model trying to use only satellite data. It just added more noise. It actually didn't help. And number 3, you can see the full model with the weather physics included. At the end, you can see that we have a slight improvement, which is better than the baseline. Basically, our model is safer. It makes fewer extreme errors, but we still haven't drastically outperformed the satellite, which led us to ask why. Is the model broken? Is the data the problem? And we end up with this conclusion. We have a solid proof of concept. We successfully built a pipeline that merges satellite and weather data, but we identified 3 major issues right now. First of all, is the satellite, it's able to see like a 10 kilometers giant square pixel when the weather station is just a tiny thing that is not able to see that much. So trying to match the average of a city to the rain in a single backyard is really mathematically difficult. Second of all, lack of radars. To fix that mismatch, we will really need like 1 kilometer radar data, which we don't have. So we are missing on that part. And also data volume. Deep learning is hungry of big data, and we only have 2024 Monsoon data. So if we could extend up to 5 or 10 years, the model will be much better doing its job. So the infrastructure is built. The next step, we will just fitting it with the proper information.
So our future aspiration includes building a prototype using US radar data to show better coverage. We are also will be sort of retraining the model every year so it becomes more accurate, even when tested with older data. Last but not least, we will try to create language tools in such a way that is very easy to understand to farmers, and possibly adding more local languages so it is accessible to everybody across the board. This is our team, Big Apple. Our team has a very diverse group. Some of us we have Sumora from Bronx Community College, along with Victor Carrion, as well as from Bronx Community College, Kazi Tassin, that's me from City Tech CUNY. We have Ariane from Graduate Center CUNY, and Lily from City College of New York CUNY. Last but not least, we'd like to acknowledge the City University of New York and the faculty members whose guidance has been instrumental to our participation in this particular hackathon. We are also deeply appreciate of their mentorship, commitment to fostering global innovation and collaboration. Special thanks to Professor Brian Vandal, Professor Paramita Sen, as well as Professor Neil Phillips. Thank you, everybody.